In this lesson, we are going to be taking a look at some of the most important very specific maps and textures, and most likely this is going to be the last lesson of this very long section. We need to wrap this section up and get on with the rest of the topics here. So let's open up our material editor. If I right click and go to the map section and vary category, you can see a list of all the available vary maps. We have used some of them frequently throughout the course up to the point, and like vary color, vary curvature, vary edge tags, vary hair info text, vary HDRI, vary sky, vary softbox, and vary triplanar text. Our approach in this lesson would be discussing only the important maps in this list from up to bottom, and based on how frequently used the map is, we're going to be spending some time on it or quickly mention what the map is for and move on. First, we have V-Ray BMP filter or V-Ray unfiltered map, and this map is obsolete right now and has been replaced with V-Ray HDRI map. But in earlier versions of V-Ray, this map was used to load displacement maps generated in softwares like Modbox and ZBrush. But right now the same thing can be done using V-Ray HDRI map with lots more functionalities. The next important map is V-Ray color map, and this map, as we have used it before numerous times, can be used to specify any custom color. And the good thing here is that you are not limited to the integer values between 0 and 255. You can actually set floating point values between 0 and 1 for red, green, and blue, and also alpha channels. The parameters are very self-explanatory, and there should be no problem. You just set the color you want in the color or temperature mode and connect the map to any input that you want in the V-Ray MTL or other materials or maps. In this case, let's create a V-Ray MTL, change the color to any color you want, and connect your color map to the diffuse map input of the V-Ray MTL. And there you have it. Next, we have V-Ray color to bump, which converts any RGB texture into a bump map. Let's select the map, and in the map slot, choose bitmap and use woodparquet.png as the map. Let's add a new V-Ray MTL and connect the color to bump node to the bump slot of the V-Ray MTL. Also, let's open up a preview for the V-Ray MTL and make it a bit bigger. Select V-Ray color to bump map and increase the height to 10 centimeters, and you can see the bump mapping in the preview. The result would be a bit more accurate compared to if you connect the RGB texture directly to the bump slot of the material. Obviously, the better approach would be to use a grayscale map and directly connect it to the bump slot of the material. Let's close this preview here and make some space. Next, we have V-Ray comp text or V-Ray composite map. It allows you to blend two textures in source A and B and blend them using one of the blending modes in the operator dropdown. For source A, let's use woodparquet.png again. And for source B, let's use BW1. And now we can go through different blending modes and see how these two textures can be blended together. And then you can connect the map to the next node in the chain. When I want to blend two or more textures together, I normally use a 3ds Max composite map or mix map, which we have used several times in this course. They're just a bit more functional and have some more options honestly. We have V-Ray curvature map, and this is one of my favorite maps. It simply looks for the concave and convex or dense and peaks of the mesh. Then the concave areas will get darker grayscale values and convex areas will get brighter grayscale values, or vice versa. Let's quickly see how it works. Add a new V-Ray light material. Use the curvature map as the light color. Assign the light material to the shader ball and run the active shade. We have subdivs, which controls the number of samples, and higher values result in a cleaner map. Sample spread controls the radius of the sampled region. If I set the value to 0.1, for example, the gradual transition becomes tighter, and as I increase it, it becomes wider. Let's set it to 0.5 in this case. We have min and max output color, and we can simply remap this range. If I change the mean output color to 0.5, now the dark color is gray, and if I change the max output color to 10, now the white color is a lot brighter. Let me use the mean output of 2 and mean output of 0 and max output of 2 here. And finally, we have scale, which basically moves the transition point between dark and light colors. For now, let's use the default value of 1 and stop the active shade for now. I think we used the very curvature map practically in the very blend material lesson, but let's do a quick example here also. I mean, the curvature map output is a grayscale map, and you can use it to control any input that takes a grayscale value, and think of it as any other black and white map. It's just procedural and generated based on the underlying mesh. Let's try to control the diffuse color of the very MTL with this map. So delete the light material. Use a mix map as the diffuse color for the very MTL. Set color 1 as pure green, and color B as pure red. Now use the curvature map as the mix amount. And now if we run the active shade again, the curvature map is controlling where is green and where is red based on concave and convex areas of the mesh. Let's stop the active shade for now. Next we have Viri dirt or occlusion map. This map is one of the very popular Viri maps. It's often used to create ambient occlusion paths or dirt in the nooks and crannies of the object. Let me add another light material and assign it to the shader ball. And connect Viri dirt to the light color input. And run the active shade. And now we can go through some of the important parameters of Viri dirt map. We have radius, which controls where the Viri dirt effect is produced. Let's try 1, 5, 10 centimeters, maybe 20, 100 centimeters. Let's set it to 10 here. You can control the radius parameter with a map. Let's use BW3 as the radius map. And you can see the effect in the active shade. And you still can control the overall radius with the value, and the map would work only in that specified radius. Let's disconnect the radius map and set the radius to 10 centimeters. We have occluded color, which is the color of the occluded areas. Unoccluded color, which is the color of the unoccluded areas. We have distribution, and if you increase this value, the dirt effect will be narrowed closer to the contact areas. Falloff controls the speed of the transition between occluded and unoccluded areas. Subdivs control the quality of the sampling, obviously. Bias XYZ will bias the normal to the XYZ axis so that the dirt effect is forced to those directions. To see the effect of the bias parameter a bit better, let's set the distribution to 10 and play with the bias values. Now let's set the distribution to 1 and bias value to 0. Effects alpha and ignore forge guy are self-explanatory. We have consider same object only, and when enabled, the dirt will affect only the objects themselves without including contact surfaces and edges. You can see when I enable it, because the material no longer considers the backdrop to compute the contact areas close to the shader ball, and it only uses the shader ball itself, we don't get the same dirt effect in the bottom part of the shader ball where it is in contact with the backdrop geometry. Let's disable it for now. We have double-sided. When enabled, rays will be traced both in the direction of the normals and in the opposite direction. This creates an effect where both crevices and edges are occluded. Invert normal allows the user to revert the effect with respect to surface normal. So instead of crevices, open corners will be shaded with the occluded color. I think this would be enough for the dirt map, and like the curvature map, it's just a procedural black and white map and can be used anywhere in your shader network. Next we have V-ray distance map. This map returns a different color based on a point's distance to an object or objects specified in a selection list. Let's copy our previous light material and connect the distance map to its light color and assign the material to the shader ball. Let's also create a sphere and put it in a close distance to the shader ball. Basically, using the distance texture, you can tell your material to use a specific color, in this case near color, for the points that are close to the defined geometries in the list down here, and another color which is far color to the points that are far away from the defined geometry. In this case, let's click on the add button and add the sphere to the objects list. And now if I run the active shade, you can see the points on the shader ball that are closer to the sphere are black, which is the color of the near color, and farther points are white, which is the color of the far color. Using the distance value, you can specify a radius outside which all points will be given the far color. Far color is the color returned by the texture for points that are at a distance greater than the radius parameters from the object specified in the list. And near color is the color returned by the texture for points that are inside the specified distance. And as I move the sphere, you can see in the active shade now, it actually affects the coloration of the shader ball. Let me just stop the active shade and delete the sphere here. Next we have V-ray edge map or V-ray edge text. This map does two things. It can show the edges or wireframe structure of the mesh, and if used as the bump map of the material, it can round the sharp corners of the object. If you remember, we actually used this map when discussing displacement mapping. In this case, let's create a V-ray MTL and for now connect the V-ray edge map to the diffuse input and assign the material to the shader ball. Now let's run the active shade. You can clearly see the wireframe structure of the mesh or its edges. You can use color to change the color of the edges here. When hidden edges is enabled, all edges of triangles will be rendered, including diagonal edges across polygons, which are normally invisible. We have show subtriangles, which when enabled, edges generated by the displacement mapping or render time subdivision will be visible. In this case, there is no displacement mapping applied to the mesh, so the edges wouldn't change. We have world width, which specifies the width of the edges in world units, and pixel width, which specifies the width of the edges in pixels. Now let's stop the active shade for now. If we disconnect the map from the diffuse input and connect it to the map input, to the bump map input, using round corners section, we can round the sharp corners of the mesh. And the radius value controls the amount of roundness that we want. Let me show you two renders with radius set to 0, so no rounding of the sharp corners, and radius set to 0.5 centimeters. The first render was with radius of 0 and the next one radius was 0.5 centimeters. And you can see in the second render the corners are round and smooth. We talked about V-Ray hair info text in depth in the lesson we discussed V-Ray hair material. We have been using V-Ray HDRI in almost every single lesson in the course, so you should be quite familiar how to use it. Next we have multi-sub object map or V-Ray multi-subtext, and it works in a similar fashion to the 3ds Max's multi-sub object material. But instead of material inputs, multi-sub object map takes textures or color inputs. As you can see, the interface also is quite similar to the multi-sub object material. You simply define as many colors or textures you want using the number of IDs, and let's in this case limit it to 5. Then you define the colors or textures that you want. Let's use 5 random colors here. After that, you simply decide how and where you want to distribute these colors. The shader ball has some predefined face IDs, so let's make sure get ID from is set to face material ID. Now let's create a new V-Ray MTL. Assign it to the shader ball and use the multi-subtext as the diffuse map. Now if you run the active shade, you can see faces that have their ID set to 1 using the first color and faces with ID set to 2 using the second color, and so on. Obviously, if instead of face material ID, use object ID was enabled and we applied this material to 5 different objects that had object IDs from 1 to 5, each object will use its specified color from color 1 to 5 as the diffuse color. Next we have V-Ray normal map or V-Ray normal bump texture, and the concept behind this map is very simple. You can define a normal map and a bump map at the same time and connect it to the bump slot of your V-Ray MTL or any V-Ray material. Let's use normal fabric.png as our normal map. And BW38 as our bump map. Now create a V-Ray MTL. Use the V-Ray normal map as the bump map input. We can open up a preview to see the result a bit better. And normal mapping is generally a bit more realistic than bump mapping, and if you are not quite familiar about how bump and normal mapping are different, you can check out the web. We discussed V-Ray Sky in detail and use V-Ray Softbox a few times in the course. And the last map we're going to be talking about is V-Ray Triplanar Texture. Let's add one to the active view. V-Ray Triplanar Texture allows quick assignment of bitmap and other 2D textures on objects that don't have suitable UV coordinates. The texture works by projecting one or more textures along the object space axis, depending on the surface normals of the shaded object. Let's quickly go over some of the basic parameters of the triplanar texture before using it in practice. We have texture mode, which specifies whether to use 1 or 3 textures for the different projection axes. We have same texture on all axes which projects the same texture along each local axis. Different texture on each axis uses a different texture along each axis. We have this texture parameter, and this one specifies the texture to project when the texture mode is different texture on each axis. This is the texture for the x-axis. Texture y specifies the texture to project along the y-axis when the texture mode is different texture on each axis. We have texture z, which specifies the texture to project along the z-axis when the texture mode is different texture on each axis. Now let's create a new very MTL and use the triplanar texture as the diffuse map. And assign the material to the shader bulb. For the texture, let's use wood parquet. And change its styling to 10 and 10. And now this texture has been projected along X, Y, and Z axis. And even if we didn't have any proper UVs on our shader ball, we wouldn't have any problem. And as you can see in the frame buffer, the texture has been projected along different axes perfectly, and the same is going to happen even if you have no UVs on your mesh. Now, if you want to project different textures along different axes, you need to simply change the texture mode to different textures on each axis. For texture Y, for example, let's use concrete diffuse.jpg. Set its styling to 10 and 10. And for texture Z, let's use grid.png. And as you can see from the frame buffer, we are using different textures to project along different axes. Blend is an important parameter. It controls the blend between different projections. Lower values produce sharper transitions between projections. Now, if I set the blend to 0 and compare the render to our previous render when the blend was, I think it was 0.1, you can see the transition between the textures now is very sharp and sudden. I'll leave the rest of the parameters for you to explore. So I think that's about V-Ray maps, and I think we are done with material section of this course, and in the next section we are going to be possibly discussing cameras. It's going to be a lot shorter compared to this very long section, so see you there.